I forgot to write this project a few years back because I've always seen these RSA keys in weird formats, and it's hard to understand what they are. So when you look at private keys, I've often saw these things: begin RSA private key, then all this garbage, then end private key. You see these in encrypted emails and stuff like that. And I never quite understood how this worked, so I decided to finally find out how it works. And here's how it works. This is the official RFC 3447. It specifies the public key cryptography standards. So you have an RSA private key is a data structure with this stuff: a version number, an N, E, D, P, and Q, all the numbers you talked about before. Here's D, mod P minus 1, and D, mod Q minus 1. Those are related to the decryption key. Here's the raw decryption key. And here's the inverse of Q, mod P. So these are all various numbers calculated from those. And I don't know why they store so many repetitive numbers, because you can calculate quite a few of these from the others. But that is the structure of a private key, a way to store basically P and Q. All right, so you can generate a random private key with OpenSSL. So let's do that. Let me get out of here and make it a little bigger. All right. So I've installed OpenSSL on here, or maybe it already came with the Mac, but I've got it anyway. So OpenSSL, I can generate RSA. And I'm going to go with the 512-bit key, which is the length they originally recommended for RSA when it came out in the 70s or 80s. It's not secure now. Like I said, it should be 2048, but 512 is enough to see how it works. That generates a key, and there it is. It tells you what E is. Like I say, you almost always use 65,537 for E, and there's the private key. So I have this mess. So that's called PEM, Privacy Enhanced Email. It's a big blob of base64 text. So I can generate a PEM file this way. This is going to generate a new RSA and put out a 512-bit key in PEM format. All right, and now I can cat it. It's key.pem. And as you see, there it is, very much similar to private key in this structure. And you can open it up with OpenSSL. OpenSSL ASN1 parse, and put your input from key. There. This gives you the data. These are the things that were stored in there, and you can just match it to the format. So I've labeled them here. The first one is just the big, this is N. Then there's E, D, P, and Q, and then those goofy ones calculated from P and Q I don't really care about. Really all I care about is N, P, and Q, and D. That's all you need. So after you know where they are, it's easy enough to find them. The public key then is N and E, and the private key is D, P, and Q. P and Q are all you need. T is also useful. All right. So now this is the private key that has all this secret information like P and Q, and you need to have that on your computer to use to decrypt messages. But when you tell somebody else the public key so they can send you data, you want just the public key, and the public key is much simpler. It's nothing but modulus and exponent. That's N and E. That's all it should be. And so you generate the public key this way. OpenSSL. I can take the private key as input and calculate the public key, which is really all it's doing is taking the N and E and not including anything else, so it's a really simple job. And there it is. In fact, this is MIIPP, and this, yeah, it doesn't quite match. The beginning isn't exactly the same, but a bunch of this is just going to be the same. This is just N and E. All right. And you can print it out and parse it. I can take the input from key.pem, the output public PEM. This will make the public out key. Instead of printing it on the screen, it'll put it in a file called public PEM, and this will print it. So all the only thing is the same thing I just did, but it's going to put it in a file. So there it is. That's the public key, and now I can open it the same way. OpenSSL pub in, take from public PEM. That will take the data from the public key and print it out. Which is here. Modulus is N here in hexadecimal, and here's E in decimal. So that is one way to extract N and E from a public key. All right. to see what these formats are. Now you can, of course, make longer keys. Here's the keys that are currently recommended, 2048 bits. This is how you make them. All right. And so that big blob of junk is a 2048-bit private key. So it's going to have N and E and D and P and Q and all those numbers in there. Everything you need is in there. And you can make the public key version of it, which will be much shorter, this way. This will make public2.pem. If I cat that, you see it's much shorter than the private key because it only has N and E instead of all that other numbers like P and Q and stuff. And you can extract N and E from it the same way. The syntax of these commands is a little screwy, but anyway, they work very well. And so there is N and E. This big mess is N, and there's E. Like I say, it's almost always 65537 all the time. All right, and I think now when you store your private key on your machine, you often password protect the private key, so if somebody gets malware on your machine, they still can't get the private key. So here you can make a encrypted private key. And this is this AES 256. Tells it to encrypt it with AES 256, the strong version of the standard AES encryption mode. That's private key encryption. So when I run this one, it's going to generate a new RSA key of size 2048 and encrypt it. It's going to ask me for a password. So I give it a password. And now every time I use it, I'll have to put in that password. So if somebody else gets on my machine, they won't be able to get that private key unless they know the password. All right. And so we can look at that one, cat key3.pem. And it looks just the same. But it tells you up here that it's encrypted. And here's the TEK-INCO. And it's cipher block chaining, so I guess this is probably the IV. I'm just guessing. That would logically be what it should be. I'm not sure if I figured out what it was. Yep, this might be the encrypted password. That's probably what it is. It's probably the encrypted password. If you remember the project we did before with encrypted virtual hard drives, there was a thing called a key safe, which included the AES key encrypted with the password. I think that's what happened here. This is probably the key safe. This probably contains the encrypted key for this, protected with a password, but I'm just guessing. Anyway, that's the encrypted version of it, and you can extract the data inside there if you do know the key with Openssl, but you have to give it the right key, right password. If you give it the right password, then you can get the unencrypted public key. All right, and so now you've got some challenges. Here's a private key, and you want to find P. Well, the private key includes everything, so if you just use Openssl, it'll come out of there. Here you have the private key, and you want to create the public key, and that will also be, this in principle contains everything, P and Q and N and all that. Here, you got to find Q, but you can see portions of this have been redacted. So you are going to have to figure out what portions are left and see if you can find enough information to determine Q. And here is the same thing. Another one, even more of it has been redacted. So you will have to see if you can find any parts of it that are any good and use them to reconstruct the rest. And I think you'll find that you have to brute force some of these characters to get something that works. So there's a few challenges just to give you some flags to turn in. And that's it. I'm going to stop this recording.